Okay, so now let's look at the issue of round off a little bit more carefully. Okay, so so again, you have this difference between f of x plus h and f of x, and I'm going to model the round-off error by saying that this is 1 plus delta 1 times the actual value minus f of x, again 1 plus delta 2 divided by h. Okay, so this is equal to f of x plus h minus f of x divided by h plus now a round-off term d delta 1 f of x plus h plus, well, minus delta 2 f of x divided by h. And so, all right, so the round-off is such that the absolute value of the round-off error, absolute value of delta I, is less than or equal to machine epsilon. Okay, so that means that this error term here, which is due to the round-off error in the worst case, right, is bounded from above. So the round-off error is bounded from above, right, by epsilon times the absolute value of f of x plus the absolute value of f of x plus h divided by h. Okay. So in practice, as I said, it's like there are two sources of error. It's like from using this finite difference approximation of the derivative, one of which is due to round-off, and the other one is due to the truncation error, which comes from your error term. Okay, so the best accuracy occurs when you let the round-off error be comparable in size. It's like to the truncation error, right? Okay, so when the round-off error is sort of approximately equal to the truncation error. Okay, and I'm going to ignore the constants, right? So, so you have that in the so in this sort of one-sided difference case, right? If you recall, the truncation error was big O of h, right? So you want h to be approximately equal to the round-off error, which is epsilon over h, right? So this is machine epsilon, I should say. Okay, which means that epsilon machine here needs to be approximately h squared, or h squared is or h is approximately square root of epsilon machine, right? Which is sort of what I had sort of said earlier. But of course, the thing to keep in mind is that this left-hand side, which is the truncation error, depends on the order of the method, right? So if the order of the method is higher than first order, then you have h to some power, and then the choice of optimal h changes, basically. Okay, so so in particular, right, if we had considered the symmetric finite difference, right, which is f of x plus h minus f of x minus h over 2h, right, this you get something. This is equal to f prime of x with an error term which is now of order h squared, right? So here you would do something different. The round-off error is still more or less the same up to constants. Okay, so now you want that the truncation error, which is now big O of h squared, is approximately equal to the truncation error, which is epsilon machine, again, divided by h. Okay, so this is telling you that h is approximately epsilon machine to the 1/3 power. Okay, and then the error, right? Then the error is like substituting this into sort of into this thing here. So it's epsilon machine to the 2/3 power. Okay, whereas in the first order method, right, machine epsilon, you want h to be approximately square root machine epsilon, and then the truncation error is like h, so the total error you get is going to scale like the half power of machine epsilon. And when you take this higher order method, it's like you get the error is comparable to epsilon machine to the 2/3 power. So this is better than the error being sort of the square root of machine epsilon. So basically, the take-home message is that if you have higher order, right, helps you get better sort of total error, right? Well, lower total, if you will, right? Even when sort of taking into account truncation error, sorry, round-off error. Okay, so that's so again, that's relevant when you're considering it's like the sort of Richardson extrapolation, because we've been pushing this higher and higher order sort of methods of computing derivatives. It's like, but again, at the back of your mind, it's like you need to worry about what the total contribution of the error is, both from the truncation error as well as the round-off error. And what this sort of it's like reasoning process is basically telling you, and you can obviously apply this to a higher order method than big O of h squared. What this reasoning process is like will show you basically is that you'll get higher order. That higher order is still actually allows you to achieve better total error. Okay, so actually let's just work that out. It's like it's not so difficult, right? So if you have a method like with the trapezoid, with the Richardson extrapolation, where you have a big O of h to the 2k method, you want this to be comparable to machine epsilon divided by h, right? So this gives you h to the 2k plus 1 is approximately epsilon machine, which means that you want h to be like machine epsilon to 1 over 2 to the k plus 1. You substitute that h back into this truncation error, you get the error, sort of the total error, is like epsilon machine to 2 to the k divided by 2 to the k plus 1, right? So as k becomes larger and larger, it's like that gets closer and closer to 1, which means that the total error gets closer and closer to machine epsilon, even in the presence of round-off error. So that's very reassuring, and that you are not doing all this work. It's like to do Richardson extrapolation to get a high order method in the sense of truncation error, and that doesn't, it's like that isn't sort of overwhelmed. It's like by the fact that you still have to deal with round-off issues. Okay, so that's a nice observation to have. All right, so let me stop here.